Hey everyone, welcome. Today we're working on the heap or priority queue questions from the LeetCode roadmap. So a heap data structure essentially looks like this. There's two variants. One is the min heap, the other is the max heap. So in the min heap, the smallest element, in this case the 10, is stored at the first node or the root node. In the max heap's case, the maximum element or the 100 is stored at the root node. So the heap has properties saying that the root node is always smaller in the min heap's case than the elements, its children, and these children are smaller than the grandchildren. So for example, here 10 is smaller than 15 and 30, 15 has to be smaller than 40 and 50, 30 is smaller than 140. So the purpose of the heap is, for example, in this case, the min heap is to access the smallest element, the 10 here, in O of 1 time. If we were to add elements to the heap, we're going to have to perform a fix-up application. Otherwise, if we pop out the smallest element, the 10, we're going to have to perform a fix down operation. So everything is reversed in the max heap case. So we're not going to focus on the implementation of fix up or fix down. Instead, we're actually going to work on the application. So let's start off with the first question, kth largest element in a stream. So design a class to find the kth largest element in a stream. So we want the kth largest element in the sorted order, but not the kth distinct element. So in this question, we need to define two functions, one to initialize kth largest and another to add a value. So when we add a value, we add this value to the stream, but also return the element representing the kth largest element inside the stream. So this problem is a heap problem because we always want to maintain a heap of the k largest elements. So we can return the kth largest always in O of 1 time. And also we need to add this new value val to the heap with each add operation. So should we use a min heap or a max heap in this case? So we want the k largest elements, which means whenever we have k plus 1 or too many elements, we're going to need to pop out the smallest element. So because we're popping out the smallest element, this min heap here gets us the smallest element in constant time. That's why we're using min heap, and then popping out the 10th element, the element 10 is going to be in O of log n time, because we need to perform a fix down. So with that out of the way, let's start coding it. So let's create a min heap with self.min heap. This could just be nums. We're going to transform nums from a list into a heap with an operation called heapq.heapify. So the standard Python library, self.min heap. So we also need to store the variable k to be used later. So self.k equals to k. So it's possible that this min heap has too many elements or more than k. So we don't need any more elements than k because they're smaller and they're guaranteed not to be the kth largest. So we can just pop them out. So while len self.min heap is greater than k. So there's too many elements, there's more elements than k, we're going to pop out the smallest element every time. So heapq.heap pop self.min heap. So what this is doing is popping out the smallest element from the min heap. So now we have the add operation. When we add a new element, we're going to want to push it onto the min heap. So heapq.heap push. We're pushing it onto the min heap, so self.min heap, and then the element we're pushing is a value, so val. So if the length is too great, so it's if len self.min heap is greater than self.k. So we have more than k elements in the heap, we're going to get rid of the smallest one. So heapq.heap pop from self.min heap. After that, we need to return the kth greatest element, which is the smallest of the k elements we have in the heap. So return self.min heap 0. So in a heap, the element to be popped out is always stored in the 0th index. So let's try running it. Submit it. Nice, that worked. So moving on to the next question, last stone weight. So we're given an array of integer stones where stones I is the weight of the ith stone. So we're going to play a game with the stones. On each turn, we choose the two heaviest stones to smash them together. Suppose the heaviest two stones have weights x and y, where x is less than or equal to than y. So the result of the smash is if x is equal to y, then both are destroyed. If they're different, then the stone x is destroyed. Remember, x is smaller than or equal to y, and the stone with weight y has the new weight y minus x. So basically, if two stones have the same weight, they're both gone. Otherwise, we keep the one with a larger weight, except we subtract the weight of the smaller one from it. So return the weight of the last remaining stone. If there's no stones left, return 0. So there's a case where only two remaining stones have the same weight, so when they smash against each other, they're both destroyed, so we return 0 in that case. So in this question, we need to always be able to access the two heaviest stones to smash them together. So that reminds us of the max heap in the previous diagram. So we're always wanting to access the greatest element in the heap. So we're going to use a max heap in this case. So max heap equals to an array, and for weight in stones. So each stone has weight, and heap q.heap push into the max heap. Remember, in Python, there isn't such thing as a max heap, so instead we're going to do negative weight to use a min heap as a max heap. So for example, if we have two elements, 1 and 2, the elements are going to be stored as -1 and -2. So when we pop, we're going to pop out -2, but -2 is actually representing the number 2, so 2 is greater than 1, we're actually popping out the greater element. So while len max heap, so while there's still elements inside this, so greater than 1, so there's 2 or more stones, so we're going to pop out these two heaviest stones. How do we get the heaviest? Well, it's going to be heap q, heap pop. So we're doing negative in front to convert this negative stored weight back to a positive weight, and we pop it from our max heap. So for y, we can do the same thing, heap q.heap pop max heap. So if x is not equal to y, so suppose the stones aren't destroyed. If they're not destroyed, then the stones will have weight negative absolute value of x minus y. So this way, it's always a negative weight we're storing, and we push this into the max heap. So heap q.heap push max heap and this weight. So after that, there's two different cases. There's a case where the length of max heap is 1 and a case where it's 0. So suppose it's 0 or equals to 0. In this case, we're going to return 0 as the question wants. Otherwise, there's one element left, so we're going to return max heap at 0. Remember, we stored the weight as a negative number, so we need to cast it back to a positive number. So let's try running that. Nice, submit it. Cool. So moving on to the next question, k closest points to the origin. So given an array of points where points I equals to x of I, y of I represents a point on the xy plane and also an integer k, we want to return the k closest points to the origin. So looking at the example here, example 1, we have 2 points, 1, 3 here, and 2, -2, 2. So -2, 2 is closest to the origin, and we want the one closest point to the origin. So in this case, we're going to return an array containing the single element -2, 2. So this question, we want to use a max heap to solve this, because whenever we have a heap of too many elements or more than k elements, we want to get rid of the largest element. And max heap allows us to pop out the largest element in O of log n time. So let's start coding that. Similar to the previous question, we're going to create a max heap equals to an empty array. And for x, y in points, so we access x of I and y of I in all the points. So the distance from the origin to this point is equal to the square root of x to the 2 plus y raised to the power of 2. except we don't actually need to square root it because we're just comparing the distances, and whether or not we square root it doesn't make a difference here in the comparison. So here we want to add this to the heap, so heap q.heap push. We want to push it onto the max heap, and what we're storing is the negative of the distance, just like in the previous question. Because there's no max heap in Python, we need to cast all the distances, or all the values we're comparing, to negative. But not only are we storing the distance, we're also storing x and y, because we need to use that in our answer. So if the length of max heap is greater than k, so if we have too many elements, we're going to pop out the greatest element, because that element is too far from the center and we're not going to put that in our answer. So heap q.heap pop max heap, so we pop it from the max heap. So now we have a heap containing the elements that are the k closest elements to the origin. But this heap is storing the distance as well as x and y, so we only want x and y, so we can just create a new list only returning the x and y for the distance x, y in max heap. So let's try running that. Cool. So moving on to the next question, kth largest element in an array. So given an array nums and an integer k, we want to return the kth largest element in this array. So again, we want the kth largest element in sorted order, but not the kth distinct element. So we need to be able to solve this question without sorting. So we want the kth largest element. That really sounds like a heap question to us, because it's very similar to the very first question, kth largest element. So in this case, depending on what k is, we want the kth largest. So the first largest is 6, the second largest is 5, so we return 5. In example 2 here, the first largest is 6, second largest is 5, third largest is 5, and fourth largest is 4. So we can use a heap to keep track of the k greatest elements inside this nums array, and just return heap pop at the very end to get the kth largest element. So this is going to take advantage of a min heap because we're always popping the minimum elements. So min heap equals to an empty array, so for num in nums, let's push it into the min heap, so heap q.heap push min heap and num. So if we have too many elements inside this min heap, so if len min heap is greater than k, we're going to get rid of the smallest element, because that's never going to be the kth greatest element. So to get rid of it, we do heap q.heap pop on the min heap. So now we guarantee that there's at most only k elements in the heap. And after that, we can return heap q.heap pop from the min heap. This gets us the smallest element. Because there's only k elements in there, the smallest element is going to be the kth greatest element. So let's try running it. Nice. Cool, so moving on to the next question. So task scheduler. You're given an array of CPU tasks, each represented by letters from A to Z, and a cooling time n. So each cycle of or interval allows the completion of one task. So every CPU cycle, we can only execute one task. So tasks can be completed in any order, but there's a constraint. So identical tasks, so for example, 2 instances of the task A, they need to be separated by at least n different intervals due to cooling time. So we can see that in the example here, n is 2. So 2 instances of the task A must be separated by 2 things between them. So we can do B between the A's, and we can also leave it idle, so doing no task at all. So we want the minimum number of intervals required to complete all the tasks. So in this example here, we have 3 instances of A and 3 instances of B. So the optimal way to do this is to do AB, let it rest, AB idle, and AB. We can also start with B, that gives us the same thing. So in the end, that takes 8 different cycles. So 6 for all the A's and all the B's, and 2 for idles. So that gives us 8. So moving on to the next one, n is 1. So we must have a break of 1 between 2 of the same task. So here we could do A, B, C, D, A, B. There's no repeats of any task, so we can just use every single CPU cycle and give an output of 6. Example 3 here, we need a longer idle time, so basically the same thing as example 1, except there's 2 idles every time. So that gives us an answer of 10. So this question can be interpreted as a priority queue question because we should always be trying to execute the task that has the greatest number of remaining cycles needed left. So for example, in example 2, A needs to be done twice, B needs to be done twice, but C and D only need to be done one time. So at the start, we should prioritize running A's or B's. So what should we do when a task is idle? Well, we can use a data structure like a queue. So a queue makes sense because it's a FIFO first in, first out data structure because we're always executing the one that requires the most cycles. So we should be pushing in the task with the most cycles first, and that's the one we want to get out first, so we can execute it again once the queue is done. So starting with that, we can just count the number of instances for every task. So we can do that with a counter in Python. So counts equals counter tasks. So after that, we can create a max heap with this counter. Max heap equals to, remember max heap, we need to do a negative because Python doesn't have a max heap. So negative count for count in counts dot values. So after that, we can use heap queue's heapify function to create that into a heap. So heapq.heapify max heap. We should always also create a queue here. Queue equals to dq. So this is the dq that's going to store the tasks that are cooling down. And we should also create a time variable to start with 0. So while there's tasks cooling down, or while there's tasks still in the heap, so while len max heap is greater than 0, or len q, so there's still tasks cooling down greater than 0, we should iterate this by increasing time first. And we should check if there's something in the max heap that we can execute. So if len max heap is greater than 0, so there's a task, we should prioritize the task that needs the greatest number of times. So we're going to pop that out. So remaining count, this equals to negative. Remember, popping out from the max heap, we need to convert it back to positive. So we negate it one more time. So heapq.heap pop from the max heap. So if remaining count is greater than 1, so if there's more than 1 instances, then we're going to need to put it in the cooling queue. If there's only 1, we can just immediately execute it and be done with this task. So putting in the cooling queue, we could do q.append, and let's append this as a tuple with remaining count -1, so we're executing 1 instance here during this time frame, and also we can execute it again after time plus n. So now if there's things in the queue, so if len q is greater than 0 and the first instance in the queue can be pushed back into the max heap, so and q01, remember the index 1 represents the time that the task can be put back into the max heap, so it's ready to be executed once again. So if q at 0, 1, so the first element index 1 equals to time, so this time means it's ready to be executed again, we should put it back into our max heap. So remaining count, and we also need that, we don't need the time anymore, so we just do underscore q.pop left. So we get the first element from the queue. Now we push it back to the heap because it needs to be executed again. So heap q.heap push max heap and negative remaining count. Because when pushing onto the max heap, we need to negate it once again. So after that, after this is done, there's no more tasks in the max heap and there's no more tasks waiting in the cooling queue. We can just return the time. So this is the total time it took for us to execute all the tasks. Let's try running it. Submit it. Nice, that worked. So this question, we're basically using the max heap to create a simulation to see how many times or how many CPU cycles it'll take to execute all the tasks. And when the tasks are cooling down, we're going to put them in a FIFO queue so that the first queue that gets put in the queue will be the first one that comes out of the queue, and it's inserted back into the max heap when it's ready to be run again. So moving on to the next question, design Twitter. So design a simplified version of Twitter where users can post tweets, follow or unfollow other users, and is able to see the 10 most recent tweets in the user's newsfeed. So we need to implement a bunch of functions here. First of all, the Twitter initializer, we should be able to post tweets. So user ID, tweet ID, so the user ID posts a tweet with tweet ID. And we can get newsfeed, so return the 10 most recent tweet IDs in the user's newsfeed. So each item in the newsfeed must be posted by users who the user followed or by the user themselves. So users always follow themselves. And tweets must be ordered from the most recent to the least recent. So we also have a follow function, so the user with ID follower ID starts following the user with ID followee ID. And there's also a matching unfollow function, which is the opposite. So the user with follower ID unfollows the user with followee ID. So in this question, we should be able to create a function to get tweets. So we need to see all the followees that a follower is following. So let's create that. That should be a map. So self.follows equals a default dictionary and initiated with a set, so they don't follow any followee more than once. And also we need a list to store what each user tweeted. So self.tweets equals a default dictionary initialized with a list. So basically the list of all the tweets a user has tweeted. And we also need a timestamp time to sort the tweets, because we always want the tweets from most recent to least recent. So we need to set a time and initialize that to 0. So when we post the tweet, we're going to want to increase the time by 1 to indicate that this tweet is more recent than all the past tweets. And let's put that into self.tweets. So self.tweets user ID, so the user with user ID tweeted this tweet. So we append it to the list, and we append it as a tuple with self.time. So it's sorted by the time and also tweet ID. So let's actually code up the unfollow and follow functions first, so we can see how get newsfeed would work. So for follow function, we can just do self.follow. So the follower ID dot add followee ID. So the set containing all the followees of a certain follower gets this new followee. Now for the unfollow function, we should check if this is actually followed. So if follow eid is in self.follows for the follower, self.follows follower id dot remove. So we want to remove this from the set. We don't need it anymore. So follow eid. So now it becomes pretty apparent how we code the getNewsFeed function, because we need to check all the different followees a follower has, including themselves, and then putting that into a min heap. We're storing a min heap because we always want to pop out the tweet with the least or the smallest self.time, because the tweet with the smallest time is the least recent and we want to get rid of that. So we store the 10 most recent tweets for the user to see. So let's create that actually we don't need self dot, we can just create a min heap, initialize that with an empty array. So follow ease equals to, so who is the user following? We can see it's a list of self.follows user ID. We're using this list cast because we stored it as a set to avoid duplicates. So now we need to cast it back to a list. But we also want the user themselves. So include user ID. We add this by casting user ID to a list first and then appending the two lists. So for followee, we want to iterate the followees and add the tweets to the min heap. So for follow e in followees, for time tweet ID in self.tweets follow e. So we're looking at the time and the tweet ID of every single followee. So we want to push that into the min heap. So heap q dot heap push min heap. We're pushing into the min heap, and what we're pushing is time and the tweet ID. So if the length of the min heap is too great, so if len heap min heap is greater than 10, that means we have more than 10. We don't need to store more than 10. We want the 10 most recent ones, so we can just start popping. So heap q dot heap pop min heap. And because it's a min heap, we're always going to be popping the the tweet with the smallest time. So that one is guaranteed not to be the 10 most recent ones. So now we can create our answer. The answer needs to be sorted from the most recent to the least recent. So when we pop out of the min heap, we're going to pop out from the least recent to the most recent. So we're going to have to reverse the answer in the end. So while len min heap is greater than 0, so while there's still things in the min heap, we can pop out the time and the tweet ID, just using an underscore here because we won't be using this time anymore. The time is only used as a sorting key. So heap q dot heap pop min heap. So we pop it from the min heap, and then we can add it to our answer. So ans.append tweet ID. With the tweet ID, we're going to reverse the answer, as we said, because the answer is from the least recent to the most recent, so we want the opposite of that. So we're going to return reversed answer. So let's run that. Heap, oh, I missed a P here. Cool. So moving on to the next question. Find median in data stream. So this is a hard question. The median is the middle value in an ordered integer list. If the size of the list is even, there's no middle value, so the median is the mean of the two middle values. So example 1 here, the median is 3. Example 2 here, there's no median, so we're taking the average of the two middle numbers, which is 2 and 3, so that gives us 2.5. So there's an example here where we add numbers and also find the medians. So in this question, we can use a priority queue because we can use two different heaps, a max heap and a min heap, to store the top half and the bottom half of the numbers. So if we use a max heap for the bottom half of the numbers, then popping from the max heap gets us the greatest number in the bottom half. We can also do the same thing for using a min heap on the top half. So taking the average of the greatest number in the bottom half and the smallest number in the top half, that gives us the median. So we can create self.minHeap equals to an empty list, and self.maxHeap equals to an empty list. So we should also define a insertion pattern. So we want the min heap, which is to store the maximum numbers or the bigger half of numbers, to be always greater than or equal to max heap. This is comparing their sizes by 1. So we want the min heap, if the two heaps have the same size, we want to be inserting it into the min heap. So first of all, when adding a number, it's possible that the min heap and the maximum heap are nothing or have 0 length. So if len self.inHeap equals to 0, remember we always want the min heap to have one greater in size. So if this is nothing, that means the max heap is also nothing. So we want to be putting it into the min heap. So heap q dot heap push self.minHeap, and we're pushing a number num. So otherwise, if the other one, so the max heap is also empty, so if len self.maxHeap equals to 0, so that means we've already put something in min heap because we see that min heap is not empty. So we want to put it into the max heap now. So heap q dot heap push self. So how do we get what number to put in the max heap? Because we don't know the relative size of the two numbers. So let's push it into the min heap first. And then using the min heap, we'll find the smaller number and put that smaller number into the max heap, because max heap is for storing the smaller half of the numbers. So let's push it into the self.minHeap first, actually. Push this number. And the lowest number We can get lowest by calling heap q dot heap pop on the min heap. So self dot min heap. And we want to push this lowest number onto the max heap. So heap q dot heap push self dot max heap. And we're pushing in negative lowest because remember, for max heap, we need to convert the numbers to their negative values. So else, so now we know that both min heap and max heap have values. So now we're not actually sure where to put this new number in. So we can get the relative size of the min heap and the max heap by comparing the greatest number in the min heap the greatest number in the max heap and the smallest number in the min heap. So let's call that low and high. So low equals to negative self dot max heap 0 because we're getting the maximum number in the max heap, so we need to cast it to a positive number again. And the high will be self dot min heap 0. So here is the greatest number in the bottom half. High is the smallest number in the top half, or the greater half. So let's see where we want to push this number. So if num is less than low, that means this number belongs in the bottom half. We want to be pushing it onto the max heap. So heap q dot heap push self dot max heap, and remember we're pushing in number as a negative. So if the length of the max heap is too great, so we always want the min heap to be greater. So if len self dot max heap is greater than len self dot min heap, this is a problem. So we want to push the highest number from the max heap onto the min heap. So basically moving one over to the min heap. So highest equals to negative. Remember we're taking negative again. Heap q dot heap heap pop from self dot max heap, and heap q dot heap push self dot min heap highest. So we're pushing this highest number that we just got out of the max heap. So otherwise, if the number is not less than low, that means we want to be pushing it onto the max heap. It belongs in the greater half of the numbers. So heap q dot heap push self dot min heap num. So if this min heap gets too big, so if len self dot min heap is greater than len self dot max heap by 1, we don't want it to be greater than 1. We don't want the difference to be greater than 1 ever. So that means we want to move a number from the min heap to the max heap. So we want to move the lowest number from the min heap, which is heap q heap pop self dot min heap. And after popping that, we want to push it onto the max heap. So heap q dot heap push self dot max heap and the negative of the lowest, because we're casting to a negative number again to use a max heap. Finally, we're done the add num function. There's a bunch of different cases in this function. So after that, we can do the find median. So find median is relatively simple. First, there's two different cases. There's one case where the median is the average of the two middle numbers, in which case the max heap and the min heap have equal sizes. So if len self dot min heap equals to len self dot max heap, so if these two different sides have the same length, that means we have the same number in the top half and the bottom half. So we can take the greatest number in the bottom half, greatest number in the bottom half, so self dot min max heap 0. Remember this should be a negative, plus the smallest number in the top half, so self dot min heap 0. Divide this by 2 and return it. So that's the case where they have the same lengths. So otherwise, if they have the same length, if they have different lengths, then the min heap is always greater. So we should just return self.min heap index 0. Let's try running that. Nice. Let's submit it. Cool. So this question takes advantage of the fact that we can have a min heap and a max heap to store the different sides of a data stream. So from this data stream, whenever we add numbers, we always want to keep the size of the left, the bottom half, and the right, the top half, to be roughly equal. We can have the the min heap be bigger than the max heap by 1, but at most 1. So that way, to find the median, we can always find this in constant time because we're just comparing the greatest number from the bottom half and the smallest number from the top half to find the median. So that's it for the heap or priority queue questions from the LeetCode roadmap. Thank you guys for watching. Hope you were able to learn something, and I'll see you in the next video.